the problem of we have a set of peers and some have resources available identified by keys, and we want to be able to efficiently find those resources. And we finished yesterday with two examples, two extreme cases. One, ask everyone, broadcast a query to everyone in the network. And the other extreme is to use a server that maintains an index, which converts basically our peer-to-peer system into a client-server-based architecture. So in fact, there are two steps involved, or a number of things, two protocols needed to manage the network. We have, for discovery or location of resources to work, we need to know about other peers in the network. So normally we need some way to manage nodes that join and leave a group, to know if I'm going to broadcast to everyone, to know something about who do I broadcast to, who do I send to, who's in the group. And in some cases we need to, for example, if we're using a server and that's maintaining an index of all the files available, then we need to publish that information to the server. So operations that, peers can search for resources, insert resources into the system. That means a node has a new file available, so somehow it needs to let others know that that's available. So we'd say that they insert that resource into the system, and similar, sometimes files may no longer be available. I was offering a file from my computer, I delete that file, it's no longer available to others. Somehow I need to let the system know or the group know, so delete resources from the system. Are the general steps that are required. So in terms of network management, how do we know if a node is in a network? If a new node wants to join a group, they need to know someone else in the network, in the system. And in general, send some message to that other existing member, P, and tell them I want to join the group. And then once a new node joins a group, we may need to reorganize the information stored at those nodes, depending upon what protocol or what approach we're using for resource location. So if we have a group of nodes, a very simple group, with P1, P2, P3 and P4, so we have in some network 4 nodes as part of a peer-to-peer system. These may be computers anywhere on the internet. They can communicate via the internet, but they've created their own peer-to-peer system for their own purpose, to share files amongst them. New node comes along, wants to join their group. How does it do so? It needs to know someone already in the group. Somehow it needs to know, for example, the address of one of these 4 nodes. And once it knows the address, it contacts them and says, I want to join the group. And if it's successful that they join the group, and then may exchange information about the resources that are available. For example, if it's about file sharing, then exchange information about the set of files that P5 has available. So we need some way for nodes to join the group, and that relies on knowing about nodes in the group. Therefore, how do we start our group? What do we do to start the group? Well, we need 2 nodes in the group to start. A node by itself is not very useful, so someone needs to know the other node's address. How does P5 know the address of one of these nodes? Either manually need to discover it, or we'll see in practice there may be a server that stores some addresses, some special addresses. We'll come back to that later. That this process of joining the network, how do we know about other nodes in the network? Well, we need to make that reasonable when we have large size networks and we'll see a server can be used. We'll come back to that one later. Similarly, if a node leaves a group, we may tell the other nodes we're no longer in the group, and then they can reorganize their information. For example, if these nodes had different resources available, so they had a set of resources available. Node 5 comes along, peer 5 comes along, and which also has some resources on offer. They need to join the group, and then somehow the group needs to learn about the resources that P5 has. So that P5, for example, may tell P2, I have R2 and R3, depending upon the approach that we use for a peer-to-peer system in the next few slides. That is, if we have a central server, then P5 would need to tell that central server that I have resources R2 and R3. If we just have a broadcast system, then it doesn't have to tell anyone. When someone broadcasts a query, it will receive that query. If it leaves the group, P5 leaves the group, it may tell other nodes, and then they may reorganize. Again, if we had a server that maintained a list of the resources, that R2 and R3 were on P5. If P5 leaves the group, it needs to tell the server, I'm leaving the group, therefore the server would delete from its index that data about P5. Then we have, okay, that's about nodes joining and leaving the group. Then we have the steps for managing resources. We can generalize into 3 different operations. We need to search, insert new data or new resources, and delete resources. Search is a query, and the query is we want to search for some resource identified by some key K. So the basic operation, I want to search with looking for some key. The result of this operation should return the set of peers that contain the resource R which match that key. So that's the general description of what a search operation should do. Someone is looking for a resource identified by key K. The system should return the set of peers that have that resource. We'll see the different approaches for doing that shortly. If a new resource becomes available, if P4 has a new file available after some time, R5, then we'd say it needs to insert that resource into the system, where we insert identifying the key of that resource and the resource itself. What does this insert operation do? Well, again, it depends upon what peer-to-peer system we're using, but it provides information such that when someone searches for K5, they will find that K5 is available at P4. So we talk about inserting a resource and similar deleting a resource, making it no longer available. One way to implement, or the general way to implement the search, the insert and delete, is to have an index of all that information. So in our example, the index maps peers, actually maps resources to peers. Resource 1 is available at peer 2 and peer 4. Resource 2 is available at peer 1 and peer 3. Resource 3 is at peer 3 4 peer 1 and 5 peer 4. We'll add that one in a moment. So if we maintain some index, then when we search, we simply provide a key, and that key maps to a resource, and then we can find the set of peers that offer that resource. So this is some index. The question is, where do we store this index? If we store it in a central server, we've basically got to revert it back to a centralized system. So we'll see in the next approach of where do we store this index information. That differentiates the different systems. And when P4 inserts resource 5, actually resource 6 is at P2. When P4 inserts resource 5, then that index needs to be updated. That is, we need to add the new entry. If someone deletes a resource, if P2 deletes the resource with key 6, in our case resource 6, then this entry in the index needs to be removed, so that when someone searches, they'll find the correct set of peers. How do we implement these steps? That's the question. And that differs amongst different types of peer-to-peer systems, which we're going to go through. There are two general ways to differentiate our peer-to-peer systems, whether it's structured or unstructured, and flat versus hierarchical. In a purely unstructured peer-to-peer system, no information is kept about resources on other peers. Each peer only manages its own information. Peer 4 only knows about resource R1 and R5. It doesn't keep an index of what other peers have. So you could think, in the simplest case, this index is stored only, the index information is stored only on the peers. We've deleted K6. If we want to distribute this index amongst the peers, then P1 has a local index which says R2 is available at P1. R4 at P1. P3 has a local index which says R2 is available at P3, R3 at P3, and similar for R2 and P2 and P4. That is, they only maintain index about the resources they store. That's a purely unstructured system. So the question is, where do we store the index information? In an unstructured system, a peer does not store index information about other peers. It only stores, you see P1, what have I done? That's P1 there. P1 only stores index information about the resources that it has. P3 only stores information about resources 2 and 3, the resources it offers. In a structured system, then nodes may store index information about other nodes. For example, if we look at the index of P4, it would have R1 is at P4, R5 is at P4. If it also stored some other information about the other nodes, for example, R2 is at P3, then that becomes a structured system. So if we store information about other nodes, it becomes a structured system. With an unstructured system, all nodes are independent of each other. They just store information about their own resources. Means if one node fails in an unstructured system, if P4 fails or leaves the network, then these other three nodes do not need to update their index. Their index information stays the same if this node leaves. But if we've got nodes storing information about other nodes, if P1 stores information about P3 and then P3 leaves the network, then somehow P1 needs to update the index to reflect the fact that P3 has left the network. So in a structured system, we need to learn and maintain information about other nodes. But if we have information about other nodes, our search can be faster, more efficient. We'll see again those two extremes of the unstructured and structured. The other classification is whether we have a flat system or a hierarchical system. In a flat system, all nodes play have the equivalent role in the system. It's a fully distributed system in a flat system. In a hierarchical system, some nodes have special functionality compared to the other nodes. There may be some special nodes in the system that perform special tasks. So in the hierarchy, so they would be at the higher level in the hierarchy, and then there's the normal nodes. With a flat system where all nodes are equivalent, it's a distributed system. Again, if a node fails, because we depend on that node no more than any other nodes, then that's resistant to failure. In a hierarchical system, if we have some special nodes, if one of those special nodes fails, then our system may not work properly. So we depend upon the special nodes more than the normal nodes in a hierarchical system. But we'll see with a hierarchical system, such is much more efficient. Search, okay, wake up. There's a spelling mistake. Search is much more efficient in the last line of that slide. Let's look at three examples of peer-to-peer systems that will show us a fully unstructured system and also a flat system, a structured system with hierarchy, and something in the middle. So three example systems. The first one, and we'll use some real protocols and applications to demonstrate these three scenarios. So there are many different protocols available, or in the past at least, and systems that, for file sharing at least, implement these different features, or can be classified as either unstructured or structured, or flat or hierarchical. We want to understand the general concepts, but to understand the general concepts, we'll go through three real examples. The first one is Napster. And you probably have heard of Napster. You may not have used it much, but it was one of the original most popular file sharing service. It had the way that it worked, it had problems, legal problems, because of the content it was sharing, but the concepts that it used doesn't have to apply to file sharing. It can be applied to any resource sharing. So we'll use that just as a simple example. Napster was an application, something you could download and install on your computer. That was the client that allowed you to join and leave networks, to insert resources, search for resources, and delete resources. So that was the application. In fact, also the protocol, the messages that are sent to maintain those resources. The characteristics in perhaps the most popular form, it was a directory-based architecture. The basic way it worked is clients or peers sent requests to some central server when they are trying to locate resources. So the query to find a resource, it was actually a centralized system, client to server. It wasn't really peer-to-peer. But once you find the resources, to then access those resources, it was direct between the clients. A normal web server, you download from that web server. That's a client-server system. Here we have, remember, in a peer-to-peer system, we're talking about two different things: search and data transfer. Search is finding the resources. Data transfer is transferring the resources, if we're talking about files, to a particular computer. In Napster, the search was using a client-server based approach, but then the file transfer, accessing the resources, was direct between peers. Let's illustrate that. Using our very simple example here. We have, so just to repeat, we have 4 clients, 4 peers. They have a set of resources available. Those resources are in fact identified by keys. So if I say resource R1, it means it's identified by key K1. So the resource may be a file, and the key may be a hash of that file, a hash value. In Napster, we have another entity, our server. So I need some more space. We have our server. So we have 4 peers plus this additional entry, the directory or the server. And when a peer wants to insert a resource, that is, make a resource available to other peers, it tells the server. For example, if peer 1 joins the network and wants to insert the resource R1, it sends a message to the server saying, I am peer 1 and I have resource R1 identified by key K1 available. And the server stores an index of the resources. So the index is the same as what we've drawn up here. It says this for each resource, which peer has it available. In fact, the index, maybe the way I drew the index here is not correct. I listed the resource followed by the peer. The key would be actually stored in the index. K1, peer 2, peer 4, K2, and so on. Because in fact we search based on key. So the index in this case that is stored at the server, K1 is available via P4 and P1, resource 1. K2 is available by P3 and P1. K3 at P3. K4 at P1 and K5 at P4. So that's what the server stores, the index of which nodes have which resources. As a new node comes, it can join the group by contacting the server. So a new node wants to join this system. We know when we want to join, we need to contact an existing node in the network. Well, in this case, we can contact the server. We could potentially contact one of the other peers, but go direct to the server and say, I want to join the group. Okay, we join the group. The resources that P5 has to offer, R2, for example, are inserted in the system. So the insert operation inserts that resource, and essentially the peer tells the server that resource R2 identified by key K2 is available at P5. So the server updates its index. And then search is easy. When peer 1 is searching for resource R3, it finds the key. So it's in fact searching for key 3. It sends a search query to the server. The server simply looks up in the index and sends back a response saying the resource identified by K3 is available at P3. So this is our basic server, client-server-based system, where the server maintains all the index information. Is it flat or is it structured or unstructured? Which one? Structured or unstructured? It's structured. Why? It's structured because some nodes store information about other nodes. In particular, the server stores information about the resources that other peers have. In an unstructured system, a node does not store information about the other nodes, in particular the index information. So this is a structured system, and it's hierarchical. There's a special node in the system, a server. So the nodes in the system have different roles. There are the peers, or the clients, and the server, or the directory. And if the server or directory fails, our entire system fails. So this is not very fault tolerant. One of the potential advantages of a peer-to-peer system is it should be fault tolerant. If something fails, the system should still work. This is not, because in fact it's a client-server system for the search. Server fails, no one can find any of the resources. Peer 1 sends a search query for K3. The server responds saying K3 is available at P3. Now, so that's the search step. The next step is the data transfer. Then it's direct between peer 1 and peer 3. So now peer 1 sends a request to peer 3. I want resource identified by key K3, and peer 3 sends back the resource, R3. That's the data transfer process, or the transfer of the resource from one node to another. That's where it's direct between peers. So we don't rely on the server for the data transfer. It's direct between peers. And we will see when we look at Bittorrent that it's similar to this approach, that the data transfer is direct between peers. And in fact, it's not as simple as you'd have to download from one peer. You can in fact download from multiple peers, or obtain the resource from multiple peers. So recall there's two different steps, search and data transfer. In Napster, search is client-server, but the data transfer is peer-to-peer.
It's between a pair of peers. Like this isn't like Bittorrent that you download from one peer can download from server peer, and it can also provide.
So yeah, in general, it's a peer obtains the resource from other peers. It doesn't have to be one other peer. For example, if if peer 1 searched for K2, it would send the query to the server. The server would send back P3, P1 and P5 as an answer. That is, tell P1 that you can find the resource identified by K2 at these 3 peers. Then peer 1 has the option of obtaining that resource from one of them or multiple. And to make the data transfer more efficient, you may be able to obtain it from multiple peers. Or if you start obtaining it from P3 and then P3 fails, then you can start getting it from P1 and so on. So because you can access in practice from multiple peers, you can be more efficient in the data transfer. We will see that in more depth and a protocol for doing that data transfer in the Bittorrent slides. Search is very easy here, very fast. Assuming the server is working, you send one query, you get a response. The server looks up, gets a response. So search is as fast as you can be without having a copy of the resource on every computer. How could we make the only way for search to be even faster would be if all peers stored all resources. Duplicate the resources, replicate the resources across all peers. That is, if we had a system, and it's not covered here, but if we had a system that, okay, P1 has a resource R1, P1 sends the resource to P1, P3. Why is this 1? Who's this? There should be 2. Is that right? Why have we got 2 peer 1s? One of them's 2. A replication-based system would involve replicating the resources across all peers. So everyone has a copy of every resource. And then search is trivial, because if every peer has a copy of every resource, then you don't have to search, because you have the resource. But of course, that requires every peer storing every resource, which is just not feasible. So this is the best case that we can practically achieve with search. Send one query to a server and the server sends a response. So very efficient from that perspective. But lacks the benefit of other peer-to-peer systems such as fault tolerance. If the server fails, then the whole system will not work because no one can search. No one can find the other peers, the peers that store those resources. And scalability, which means that as we increase the number of nodes in the system, the load on the server increases. Because now if we move from 5 peers to 500 peers, the index increases at the server. That becomes harder to manage. And the load, the queries going to the server, increases. It becomes a bottleneck. So that's the problem there. It doesn't scale well as you increase the number of nodes. Let's look at it. So that's one extreme, really, of a peer-to-peer system. In fact, the search is client-server, but the data transfer is peer-to-peer. And as we mentioned that yesterday, you have a server that stores the index. The other extreme, which we also mentioned yesterday, is broadcast. And Nutella is one example of a system that in the past used this broadcast approach. It's an unstructured peer-to-peer system with a flat architecture. Ignore loosely coupled, we're not talking about that anymore. Let's leave that one here and draw the same network, but looking at it from the perspective of Nutella. We have a set of peers. try and get the same set of peers, but what have we got? P1, P2, let's add a few more peers. We have 8 peers in this example, and those peers have some resources available. Let's just randomly select some resources. So some peers, the peers have some resources available. It doesn't matter what these values of resources are. If you want to copy this down, then the main one we need is that R5 is on P2 and P8. We'll use that in the example. This is a unstructured peer-to-peer system. Each peer only stores information about the resources it has. So if you think of the index and the structured approach, the index was stored everything on the server. In this approach, each node maintains its own index. I will not draw it for all nodes, but the index for P4, for example, would be K2 is available by P4 and K10 is available by P4. That's it. That is simply P4 knows about the resources that it has. So to reach K2, P4 has it. To reach K10, P4 has it. P4 does not store any index information about the other nodes. And same for each node. They have basically indexed their local resources. That means it's simple to maintain this index. In our Napster-based approach, when a new node came in, when P6 came in and had a resource to offer, resource 10, it needed to inform the server. The insert operation, which inserts that resource into the peer-to-peer system. In Napster, we need to send a message to the server saying, I have this resource available, and then the server updates the index. And if someone deletes a resource, then again, we need to tell the server this resource is no longer available, and the server updates the index. So that requires some steps for insert and delete. In this approach, if a resource becomes available at P4, R3 becomes available, P4 doesn't have to tell anyone. It just updates its local index. So that's very simple for inserting and deleting data. If R3 is no longer available, P4 just deletes this index information. It doesn't have to tell anyone else. Similar, if a node, in our Napster approach, if a node leaves the network, P6 leaves the network, then somehow the server needs to update its index to reflect that resource 10 is no longer available at P6. So as nodes join and leave the network, in this approach, the server needs to learn about that. If a new node joins our Gnutella network, then again, it doesn't have to inform any other node. It just maintains its local index information. That keeps the management parts simple. It's a flat architecture. All nodes are treated equally. There's no special nodes. There's no special server here. How do we search then? Then, as we mentioned yesterday, we use a broadcast-based approach. This describes some of the steps. We'll just go through it in general first. Example, P6 wants to search for resource identified by key K5. P6 is looking for resource 5. That's the challenge. Then we broadcast a query, or this search query, to all of the other nodes, saying, I'm looking for K5, let me know if you have it. So that's the basic approach. How do we implement that? Each peer maintains some information or links to several other peers. So these are 8 computers on the internet, anywhere on the internet. They have IP addresses, the application's running on some port number. We have where is it? A peer will maintain links to some other peers in the system. So if a new peer joins the network, peer 9 joins, then what it does is that it needs to contact some other peers already in the network, and it does that by using some what's called ping pong messages. It sends a ping to some other peer which may respond telling that peer it's available. So the idea is that peer P9 needs to discover other peers, so it sends some messages to other peers and they will respond if they're available to act as one of its neighbours. So what we need to do is form a topology where each peer has a set of neighbours. For example, each peer has 4 neighbours. For this to work, peer P9 needs to know about one of the peers in the network. How does it do that? Again, we may need some initial server, some initialization server. P9 needs to know the address of someone to send a ping message to find out some neighbours. How does it get one of those addresses? It needs to manually discover it, or we have some server that automatically maintains those addresses. Some special server that records the addresses of some of the nodes. Some server records the addresses of P8, P7, P3. The server has a well-known address, a domain name or an IP address. P9 wants to join the network. It contacts this server and tells me, tell me some of the peers that are in this system. Server responds to P9 saying P8, P7 and P3. That is the IP addresses of those peers. So now what P9 does is contacts those using this ping pong approach. Basically send a request and get a response to P8, P7 and P3 here. Why did I choose those 3? No specific reason. Let's change P3 to P1. That is, they don't need to be nearby. They're just any other computer on the network. P9 contacts a set of these other peers with the intention of finding neighbours, finding nodes that will be its neighbour in the system. So it may contact P8 and basically say, will you be my neighbour? P8 may respond yes, or it may respond no because it may already have enough neighbours. But it may respond with a message saying no, but try to contact P3 and P5. They may be your neighbours. With the idea that each peer has a set of neighbours. And in this case, let's see how many neighbours we have. I'm not sure how well this will work. Let's leave P9 out of it for a moment. And I've just connected some of these peers together, not via links in a network, but conceptually they are neighbours. These are 8 computers distributed across the internet. Doesn't matter where they're located, but they need to know about some other peers in the network. For example, P6 knows about P1, P4 and P5. When I say knows about, I mean they know at least the IP address of that peer and probably the port number because it's running some application. How do they know about those? Well, when they join the network, they ask one of the other peers about who's in the network and who they can create neighbours with. How do they learn about the other peers? There's some initialization server that keeps track of some of the peers in the network. So P9 joins the network, wants to join. It says it doesn't know about any computer in the network except this special server. P9 contacts a server and says, tell me about some of the peers, tell me their IP addresses. Server responds with P8, P7 and P1. Then P9 contacts P8, P7 and P1 and saying, will you be my neighbour? And one of them may agree to be, or one or more may agree to be. If they don't, then at least P8 may respond saying, so it says, sends a ping message, sends a response, a pong, and if it says no, I will not be your neighbour, but here are a list of other peers that I know about. Try P3 and P5, because P8 knows about, or try P7, P3 and P5, because P8 knows about those 3, because those 3 are the neighbours of P8. So the idea is to find some other peers to act as your neighbour. Ask some peers, they may respond with their neighbours, and then we will ask P5. If P5 accepts, then it has a neighbour. If not, P5 may respond, try P4 and P6. And then eventually P9 will have a set of neighbours. I'm going to remove P9 just to keep the network down to 8 for our next examples. I've tried to draw this so that each node has 3 neighbours. You see each peer has 3 links, 3 conceptual connections to other nodes in the network. P2 has 3 neighbours. I think all of them have 3 neighbours. P4 doesn't, so there's some other node down there. It's not possible to draw all. So the idea is that all nodes will have approximately the same number of neighbours, the same number of connections. A common value is 4. So a new peer joins the network. He wants to find, say, in our case, 3 neighbours. That's a parameter of the system. 3 nodes that we have permanent connections to, that we know their IP address. Now, once we've established our neighbours, we know about our neighbours, then we want to search for some resource. So our example is P6 wants to search for the resource identified by K5. We use a broadcast-based approach or a flooding-based approach. Our query, some query message is sent. First P6 checks, does it have it in its index? Well, no, P6 does not have resource R5. It sends a query to each of its neighbours. The query goes to P4, P5 and P1. That is the 3 neighbours of P6. A query searching for K5. Those 3 neighbours, when they receive the query message, look in their index. That is, they check, do I have the resource identified by K5? Do I have resource R5? P4 does not. So P4 then sends the query to its neighbours. P4, in our case, only has one other neighbour, sends to P5. P1 does not have R5, So it will send the query to its neighbours. P1's only got 2 as well. So we could connect P1 and P4 if we wanted 3 for each. Query goes from P6 to P5. P5 does not have resource R5. So P5 would send to its neighbours. So this is just a flooding approach that we've seen in data communications. Send to all of your neighbours with some exceptions. Do not send back to the person who just sent to you. Let's look. P8 receives the query. P2 receives the query. And we have a hit in this case. We're searching for a resource identified by K5. P2 has a resource R5. That is, it has the resource identified by K5 and can send back a response. So we've found the resource in this case. So the response comes back and saying the query for resource R5, you can find that resource at P2. And then once P6 knows that it's at P2, it can perform the data transfer. Similar, P8 will respond as well, because it also receives the query, because it also has the resource. So we may receive multiple responses or have multiple hits. The slide talks about the specific types of messages, but for this we just need to know the general concept. And the general concept is each node finds a set of neighbours, other nodes it knows the addresses of. To search, we flood a query through the network. And we should find the resource. Compare it to our previous example using Napster, where we had a centralised server. Managing the resources when a new node joins and leaves the network in Gnutella is easy. A new node is in the network. It doesn't need to. No other nodes need to update their index. In Napster, when a new node joins the network, they need to inform the server, and the server updates the index. So there's some extra complexity in Napster. Search in the Napster approach, you send a query. P1 sends a search query to the server responds with the answer. Here, we need to do flooding. Send a query to my neighbours, they send to their neighbours, and so on. Search is much more inefficient in Gnutella. Slower to get a response, and more packets are sent through the network. Expand this to 100,000 nodes across the internet. To do a search, you need to send many packets through the internet. In Napster, you send just 2 packets, the search and the response. Here we send potentially thousands of packets just to do one search. So search is very inefficient. Because the Gnutella approach is a flat architecture, if a node fails, the network will keep working. If P3 leaves the network, then our query will still get through, so long as we have enough nodes to have some connectivity. If P3 leaves the network, our query will still get to P8 and P2. If P2 leaves the network, no longer in there, our query for K5 will still get to P8 and P8 will respond, so we'll still find the resource. So much more tolerant to faults in the network, nodes failing, for example, or leaving the network. Whereas in Napster, if P2 leaves the network, everything will keep working, but if the server fails, search doesn't work. So we have high dependence on the server in this first approach. Yep.
If one node leaves the network, does it have to inform the server?
If a node leaves the network, does it inform this special server? Not necessarily. This server is only used for the initial joining of a node to the network. So the server needs to know about some peers. Whether they actually exist in the network at this point in time or not probably doesn't matter if it has enough peers. Imagine there are 100,000 peers. If the server has a list of 100 peers of those 100,000, and maybe some of them have already left the network, so they would need to learn about that later. But if some have left the network, then still it has 90 odd entries in here. This server is only used so when a node wants to join, it contacts the server. The server tells it the list of those 100 peers. Then this new joining node contacts some of those. Let's say it chooses 3 of them to contact, and then it's learned about some of the peers, and then it can learn about other peers through those 3. So it's nice to update the server, but not needed in practice. It would eventually be updated if someone contacts a peer on the server's list, but that peer doesn't respond, then they could inform the server and update the server. So in any system, we need some way to know about an existing peer in the network. And the common way is to use some initialization server or bootstrap server. But we don't want to depend upon it too often. In practice, we can replicate this server. Instead of just having one such server, we can have multiple servers across the internet that maintains lists of some peers in the network. As with flooding that we saw in data communications, when we flood our query, we can have certain optimizations. We know with flooding, when we send a message, there are many packets sent to deliver that query. That's very inefficient. To reduce the number of packets sent, then we can do some form of selective flooding, limit the number of hops. Let's make sure our search query will not go more than 2 hops, for example. So it goes to P5, P8, we get a response. If P2 didn't have resource R5, it would go to P1, P2. P2 would not send it on any further if we have a hop limit in our search query. And there are other ways as well. So the problem with Gnutella, this approach, is that broadcast or simple flooding is very inefficient. If, in our example, we had 3 neighbours, if the number of neighbours is 4, C is the number of connections each node has, the number of neighbours. If it's 4, and we have a flooding approach which has a time to live such that we will not send more than the time to live number of hops, that is 7 as an example. That is, I'll send 7 hops, no further. Then a single query may generate 26,000 messages in the network, 26,000 packets, because the first node sends to 4 neighbours. Each of those 4 neighbours then send to their neighbours. All of them send to their neighbours, and we do that 7 times. It's around 26,000 sending. So in Napster, the query, just 1 message is sent. In Gnutella, in that example, many messages are sent. That's very inefficient to search. Each node that receives a query needs to check its database. That takes some time as well. P2 receives a query, check the local database or its local index. So ways to improve is what's called expanding ring search. You set the time to live or the hop limit to a small value, let's say 1. P6 sends to its 1 hop neighbours, 1, 4 and 5. If they have the resource, they'll respond with a positive answer. If they don't, they respond with a negative answer saying, no, I don't have it. They do not forward it on with a TTL of 1. So we send to our 1 hop neighbours. If they don't have it, then we try and send again, but set the TTL to 2. Send to our 2 hop neighbours. So expand the time to live or the hop limit until you get a response. That's a way to increase the efficiency. Or some selective flooding, a random walker. Do not send to all your neighbours, send to a random selection of your neighbours. Send to P4 and P5. They send to a random selection of their neighbours and so on. So we don't do full flooding, we do selective flooding. Again, reduces the number of messages sent, but increases the search time. It takes longer to find someone who has that resource. So two basic approaches. Napster, which is a centralised approach. The server maintains the full index. Gnutella, where the index is stored only on the nodes that have those resources. A fully unstructured approach using a flat hierarchy. And let's look at one example which joins the two, something in the middle. Fast track is one example. It's a hierarchical peer-to-peer system, and it's what's called the super-peer architecture. We combine parts of the previous two approaches. What have we got? I'm going to do it on the board. You've got this in front of you. The approach is to take advantage of the centralised server in that search is fast, if we have a centralised server, but also try and take advantage of the fault tolerance available in Gnutella, where if a node fails, the system will still work by trying to combine them. Let's see how fast track or a super peer based approach works. We have a set of peers. I'll draw in a moment, I'm going to draw a set of peers in our network, and they are arranged to find neighbours with a super peer. So for example, peer 1, peer 2 and peer 3, there's some nodes in the internet, connect to a super peer A in our case. Again, they don't have to be necessarily in the same geographical location. They may be just anywhere in the internet, but they form some arrangement such that each peer is associated with a super peer. And we have multiple super peers. In my example, I'll put 3 peers per super peer. So this is the set of nodes in our example network where we have a hierarchical structure because we have some special nodes called super peers. And peers are associated with one of the super peers in the network. And the super peers will form connections with other super peers in the network. where what we get is a combination of our Napster centralized server approach between peers and superpeer, and the Gnutella approach, which forms the network amongst the superpeers. That is, we will use flooding to send queries between superpeers, and we'll use a query that just goes to the directory or the server for peer to superpeer. Let's see how that works. So again, peers have resources available. I will not draw it for all of them, just a selection. For these three peers, for example, peer 2 has resource R2, P1, R1 and R4, P3, R5. The other peers also have resources. They treat their local group as a client-server-based system, and the superpeer maintains an index of those resources. So the index at superpeer A is K1, that is the resource identified by key K1. In other words, resource R1 is available at P1, K2 at P2, K4 at P1, and K5 at P3. That is the set of resources identified by their keys at the nodes connected to that superpeer. Similarly, other superpeers would maintain indexes for what their local peers have available. Let's, for example, we'll draw an index for superpeer E. K1 at P14, K3 at P15, K5 at P13, and K6 at P14. So the index stored by superpeer E. And now, all right, how do we get those indexes? Or how do we first establish this association between peers and superpeers? Similar as before, a new peer joins the network. A new peer, who are we going to draw? If peer 11 wasn't there, peer 11 joins the network, they want to join the network, then they need to contact some other peer in the system, some other node in the system, and join a local group. So basically they need to find a superpeer to connect to. What do they do? How does P11 join a group? How does P11 join a group? It needs to know the address of some other peer. What's it do? Some mechanism to contact a superpeer. What is that mechanism? So you're right. If we want to join the network, we need to join some local group, that is, contact a superpeer. So what do? In Gnutella, what do? If we wanted to join the network, we contact some special server. The same approach here. We contact some special server. That special server is referred to as what? A superpeer. Okay? So some special server that maintains a list of superpeers. It knows about SPA, SPB, and so on. When I say knows about, it knows the IP address and any other identifying information about those super peers. So P11 wants to join the network. It contacts the super peer saying, I want to join the network, and the super peer can send back a list of those super peers. And then P11 can choose one of them to contact. It may not just contain a list, it may contain information about the current status of those super peers, how many current peers are in their group and so on. But the basic approach is contact a special server to learn about existing nodes. In this case, learn about existing super peers. Let's say it chooses to communicate with super peer D. So it sends a join query to super peer D, which responds positively, and then it publishes the resources it has available in the index of super peer D. That is, if P11 has some resource to offer, then that resource, or the index in super peer D, is updated. That is, we insert that resource into the system. So we join and update the index in the super peer. I will not draw the index for this one. So that's how nodes join. If a node leaves, again, it should tell the super peer, and the super peer will delete that information from the index. To search, P1 wants to search for a resource identified by key K5. We use the centralized approach within the local group. P1 sends a query to the super peer saying, I'm searching for the resource identified by K5, sends it to the super peer A. This looks in the index, K5, P3 has it. Sends back a response, contact P3. So we've found it immediately. If one of the peers inside this group has the resource, then search is simply send to the super peer, get the answer. Same as here, send to the server, get the answer immediately. So search is very fast if a peer in your local group has the resource. Very fast and very efficient in terms of only one request is sent. It's not flooded through the entire network. If we're searching for K6, now we want a different resource, resource 6. We again send the query to the super peer. We're searching for K6. Super peer checks its index, K6. I don't have K6 in this local group. So now we use the flooding-based approach, but just between super peers. Super peer A sends a query to its neighbours, neighbour super peers. They check their indexes. So C and B have an index. If the resource is in their index, they will respond with the answer. Then, if not, they will forward the query on to another super peer. And if B, C and D do not have K6 in their index, eventually the query would get to E. It is in the index, K6. E will respond with P14 because P14 has resource R6. So flooding between the super peers, direct between the peer and the super peer. Flooding of the query between super peers if necessary. To initiate, we send a query direct to the super peer. So it's a combination of both approaches, and it's a trade-off in terms of efficiency and fault tolerance. We now have some special nodes. If super peer B fails, what happens? If it fails, that computer acting as super peer B, fails instantly, what happens to our network? Will it still work? If I send a query for K6, it will go to my local super peer. If it doesn't have the response, it will broadcast to other super peers. If B wasn't there, it would go to C, go to D, and go to E and would get the response. Of course, in a real network, we'd have more than 5 super peers. So we'd have more than 2 connections. We could have more, 3, 4 connections. If one fails, we can use the other paths. If a peer fails, no problem. We just need to update the local index. If a super peer fails, we can still go to other super peers. So the failure of these special nodes can be handled. If a server fails in Napster, the entire network will not work, or the search will not work.
If one of the super peer fails, what about the peers that are connected to the super peers? Will it find new super peer to connect with, or what would it?
Yeah, so if super peer B fails, then P4, 5 and 6 need to do something because they're no longer part of, they no longer have a super peer. Yeah, join the network again. That is, P4 now no longer has a super peer. Join the network by contacting the super peer saying, tell me a list of super peers, and it will try and find another one. So if a super peer fails, the local peers need to update and find a new super peer. Even though we do flooding between the super peers, imagine we have a network of 100,000 nodes. In Gnutella, we do flooding between those 100,000 nodes. In the super peer architecture, if we have 100,000 nodes, maybe just 100 are super peers. And each super peer has 1,000 local peers attached to it. So 100 super peers, 1,000 peers attached to each super peer. Therefore, it's highly likely to find a response when I contact my super peer. And if I don't, we use flooding between the super peers, but still it's only between 100 nodes. Flooding across a smaller network is much more efficient than across a larger network. So there's the advantage. And in fact, if we send a query to super peer B and there are 1,000 nodes attached to super peer B, the index will be quite large. So again, it's highly likely that B or a peer attached to B will have the resource. So much more efficient in search here. We gain the efficiency in search that we found with Napster and the fault tolerance we found with Gnutella. If nodes fail, the system still works. It's a trade-off between the two. So we've gone through 3 approaches for implementing these operations of a peer-to-peer system. We've focused on the search operation, but there are 2 things: locating resources and then obtaining those resources, the data transfer. We've focused just on how do we find the peer that has the resource. Once we find the peer or peers that have the resource, then we may need to transfer data from those peers to the node looking for it. We haven't really spoke about how to do that. To locate resources, we maintain some index. The question is, where is that index stored? In Napster, it's stored in a centralized server. The entire index mapping keys to peers is stored in one location, or a central server. In the Gnutella type systems, the index is stored just on the nodes, on the peers. And each peer only indexes its local information, and it becomes an unstructured system. In the super peer architecture, the index is on the super peers. It's distributed amongst multiple peers. And we search, we have a combination of going to a server or a super peer and flooding the query through the network. And we've seen some special cases when we want to initially join the network, we need to know about other nodes in the network. So in all of these cases, there is some server involved. Even in Gnutella, we need some special server. But it's only for joining the network. So if this server fails, the nodes in the network at that point in time can keep communicating, but no nodes can join the network until the server is back up again. So even though they have servers, the super peer, the server in Gnutella, that they're not highly dependent on these servers, only in the join phase. And that's the three main approaches we're going to go through for search. There's one more, but we'll return to that later. Any questions on these three? We've used Napster, Gnutella and Fast Track as examples, but the concepts are applied in other systems. And the concepts of centralized server, full flooding, or a mix can be applied to any system. Any questions on those three concepts, the three different approaches? You should be able to identify the trade-offs for each of them in an exam question, for example. What's the advantage of one against the other? Let's return back to our slides. Here we have our ordinary peers, super peers and super peers. So the slides cover what we spoke about. There's another approach called distributed hash tables. We'll go and move on to something else first, Bittorrent, and then come back to hash tables later. That requires much more time. We'll see it's a flat architecture, but it's a structured system. Gnutella was a flat architecture but an unstructured system. We'll come back to distributed hash tables later. What we want to go to now is look at how do we transfer data efficiently. Once we can find peers that have the resources, if we're talking about file sharing, how do we efficiently get the resource, the file, from peers to the one who's looking for it? The data transfer part. And that's so we're going to look at how Bittorrent does that. So in the next set of slides that you have. Where? Finally, I'm remembering to record who's here. Let's look at Bittorrent as an example of data transfer in a peer-to-peer system. How we can make it more efficient than using just a server. We won't look at how search works in any detail. We'll look at how we can transfer the data. To show the benefits of downloading files from peers rather than a server. And to show that, we'll use Bittorrent as an example. There are other protocols that do this, and show the basics of how Bittorrent protocol works. Before we get into how Bittorrent works, let's just look at a very simple example to explain the motivation of this. Comparing, the objective is to download a file. I'm a computer, I want to obtain some file, some resource, and download that. The two basic approaches I have, as you do in the web normally, is you go to a server that has that file and download the file from that server. Okay? A client-server based approach. We'll look at an alternative, a peer-to-peer based approach, is to, if that file is distributed amongst other clients that have already downloaded it, then download from them. And we'll just use a very trivial or contrived example to demonstrate the differences. Consider a server has some file that our client wants to download. I have to draw this. I've just made up some numbers so we can do some calculations. We have a 1000 megabit file, not megabyte, megabit, so it's easier to calculate. Stored at the server. And we'll use a client-server based approach. That server has the file. Anyone who wants the file goes to that server and downloads from the server. Our server, we have this 1000 megabit file. And we have a number of clients, that is a number of users, want to access that same file. Do we say 5 users initially? Client 1. 5 initial users, and sometime later 100 more. So in fact we're going to have some more clients. So many, in more than 100 clients want to access that file, but at different times. Assume all, what do we say? All users can receive at a maximum of 1 megabit per second. That is, the link or the path between client and server has a bandwidth of 1 megabit per second. Let's draw this differently. It's part of the internet. There's a router. Each client, so somewhere on the internet, have a local link, and here's our cloud, which is our internet, our IP network. All the clients connect to the internet, and so does the server. And the links, all links are 1 megabit per second links. That is, this one is 1 megabit per second, full duplex. That is, we can send at 1 and receive at 1, and so are all these links. All links are 1 megabit per second. In this scenario, to get some numbers as an output, initially there's 5 users. They want to download the file from the server, all at the same time. So these 5 clients contact the server, send a request, and the server starts sending them the file. So that is, they start downloading the file. So just 5 users start downloading the 1000 megabit file. Even though the users have 1 megabit per second links, the server has just a 1 megabit per second link. If there are 5 users, if the server is sending that file to 5 clients, then of that 1 megabit per second link that the server can send at, then if it's sending to 5 clients at the same time, then it's sending at a rate of 200 kilobits per second to each of those clients. That is, share equally amongst those 5 clients. Each user can receive at a maximum of 1 megabit per second. That is, the links here are 1 megabit per second. The server can send at 1 megabit per second. The link here is 1. The server is sending to 5 different users at the same time. So the server is sending at a total of 1, but per user at 0.2 or 200 kilobits per second. So actually C1 is receiving at 200 kilobits per second. So is C2. And so is C5. We have 5. Because we must share this link amongst the 5 connections. We're sending to 5 at the same time, then we share that 1 megabit per second amongst 5. So from each user's perspective, if we need to download a 1000 megabit file and we're receiving at a rate of 0.2 megabits per second, then it turns out to be a total time of 5,000 seconds to download for those 5 clients. That is, you've got a 1000 megabit file. At 1 megabit per second, it would take 1000 seconds. But since we're sending it to 5 users, it's going to take, for each user, 5,000 seconds. Or the other way, if we sent it to user 1 first, it would take 1,000 seconds. And then if we sent it to user 2, it would take another 1,000 seconds. And then user 3, 4, 5. In total, it would take 5,000 seconds. So if you sent 1 user at a time, in total it takes 5,000 seconds. Everyone sign their name. Because we must share this amongst the 5 users. Any questions on that? Why we get 5,000? Make sense? Okay, does it make sense? Okay, very simple. Now, 5 users have the file. Sometime later, 100 users. This file becomes popular. They learn that this file is popular. These 100 other clients go to the server and download the file. Same approach. It's a 1000 megabit file. The server needs to send to 100 users at the same time. So effectively, this 1 megabit per second link here is shared amongst 100 users. So for each user, we've got 1000 megabits being received at a rate of 1 kilobit per second. 10 kilobits per second. 1 megabit per second is the sending rate, but we're sending to 100 different users, so 1000 divided by 100 gives us 10 kilobits per second per user or per client. 1000 megabits at a receiving rate of 10 kilobits per second is 100,000 seconds. So user 6 receives it. They start and it takes 100,000 seconds before they receive the entire file, and same with all the other users. So this is the client-server approach where everyone accesses the file from one server. It takes a total of 5,000 seconds at the start for the first 5 users, and then when it becomes popular, each user it takes 100,000 seconds. Let's look at an alternative approach. Let's use a peer-to-peer approach, or the approach used in Bittorrent, and see the advantage. What we're going to do is those first 5 users, they'll download from the server, and then once they've downloaded the file, when someone else wants to download it, then they would download from those first 5 users instead of the server. So same scenario, 5 users download the file at the start, all from the one server. Therefore, it's going to take the same 5,000 seconds per user. Client 1 downloads, Takes 5,000 seconds, 2, 3, 4 and 5. So that's the same as the previous case. But what's different now is that these next 100 clients, instead of contacting the server, contact one of the clients that already has it. One of these seed clients. What happens in that case? Okay, it's as if now we have 5 servers. From the perspective of these 100 clients, there are 5 servers that have the file. Each have the 1000 megabit file. So of the 100 clients, on average, 20 clients can download from this client 1, the file. Another 20 could download from client 2, and so on, and the final 20 could download from client 5. If the system is perfect, we can direct the clients that want to download to one of those 5, such that we share the load amongst those 5 clients. So now we have 20 clients here downloading the file from client 1. Client 1 can send at a rate of 1 megabit per second, shared amongst 20 users, so we get our 1 megabit per second divided by 20, which is our 50 kilobits per second. So for those first 20, they can download at an average rate of 50 kilobits per second, because we've got 1 megabit per second divided by 20 users. 50 kilobits per second per user, 1,000 megabits takes 20,000 seconds for each of these 20 users to download. And at the same time, the next set of 20 users are downloading for client 2 at the same time as the first are downloading from client 1, and at the same speed, because client 2 has a 1 megabit per second link shared amongst the 20 users. Those 20 users, per user, it takes 20,000 seconds to download. And the same for the remaining 60 users. In summary, the first 5 clients, same as in the previous example, take 5,000 seconds to download from the server. The next 100 clients do not download from the server does nothing. They download from the first 5 clients that already have the file. And because we effectively have 5 servers here instead of 1, we've got an increase of a factor of 5, or a decrease in the time to download of a factor of 5. We've reduced it from 100,000 from the previous case down to 20,000. So in total, for all 105 clients, it takes 5,000 plus 20,000, 25,000 seconds. In the previous case, where everything went via the server, it takes 5,000 plus 100,000, 105,000. The numbers are just made up there to illustrate that in this perfect case, by downloading from those that already have the file, we can increase the speed for the users or reduce the download time. It's the same as using multiple servers. It's just that the clients that download the file become servers. The more servers we have, the more we can be downloading in parallel. And that's what Bittorrent allows us to do and other peer-to-peer data transfer systems. Don't all contact the one server, contact other nodes that have the data that you want to access. Of course, in that example, so we saw that the total download time was much shorter than using just one server. The actual performance depends upon different factors. How many servers do we have? How many initial servers? How many of these seed users, these first 5 users? I chose 5 in this example. Why 5? Well, just to calculate, the number of seed users, the more we have, the more we can share the download rate amongst the subsequent users, the faster it will be. And of course the number of downloading users. So we basically have 3 types of users: the original server, the seed users, and the downloading users. The number of them impact upon the performance gain. And also these speeds. I chose a simple example where everyone could send at 1 megabit per second. In reality, the nodes have different upload and download rates. So some computers will have high speeds here, some will have lower speeds. So the speeds able to download and upload from, especially from the perspective of the clients or the seed users, is important. And another thing that we can use to improve performance is by structuring the file into multiple pieces. In our example, we had a 1000 megabit file, 5 users downloaded it, and then the next 100, once it was downloaded, could download from those 5. What if we broke this 1000 megabit file into 10 pieces? What it means is that we download piece by piece. Client 1 downloads the first piece. As soon as the first piece is available on client 1, client 6, 7, 8, 9 and 10 can start downloading that first piece. We don't have to wait for the entire file to be downloaded before these next set of users start downloading. That is, by breaking it into pieces, we only have to wait until a piece is downloaded instead of the entire file. So that's another way to improve the time to do the total download. And we'll see that's what Bittorrent does as well. That is, as clients are downloading the file in pieces, they are making those pieces available to other clients to download from them. And they can do that in parallel. So this is a common approach used in peer-to-peer file sharing, and BitTorrent is an example. What are the advantages? We're not always dependent on the original server. In the initial stage, the seed users downloaded from the server, but after that, we didn't depend upon the server. If the server fails after the seed users have a copy, the other users can keep downloading from the seed users. But if we had a pure client-server system, we always rely on the server. So the advantage here is we don't always rely on the original server. And that gives us redundancy because we actually have multiple servers now that these 5 seed users have downloaded the file. We have multiple copies of the file. And performance, as we've seen. We no longer have the server as the bottleneck for performance. The disadvantages, it relies on the participation of other users. That is, for this to work, these 5 users, once they've downloaded the file, must be willing to allow others to download from them. If not, then we have no advantage there. As the number of these 5 users, if we decrease this down to just 2 users, then the performance advantage is much smaller. If it's down to 1 user, then it's the same as using a single server. So the number of seed users impacts upon performance. And another disadvantage is there's no central control of access to content. When we use a pure client-server system, the server controls who is allowed to access that file. You can have to supply some username and password, for example. The server controls that because everyone contacts or goes through the server to access the file. But in the peer-to-peer system, if these 5 are allowed to access the file, the server can control that, but now the server has no control on who accesses the file from these 5 clients. So it's impossible to control the access to the content in that case. Who accesses it? And also, there's difficulties in finding the content. We no longer have a central server that indexes all the files. The files are distributed amongst different clients. And that's why we need the previous approaches that we've gone through for searching for files. And other issues arise. security, privacy, accounting, legality, and all many other issues. Legality is about, well, the content. The content in many peer-to-peer file sharing systems may be illegal in different countries, but the technologies that we use here are independent of the content. We could use such a system inside SIT to distribute lecture notes or distribute large files that we want to share of videos and so on. So it's independent of the content. We will look at one particular, just one or two more slides so we can go on to Bittorrent next week. We'll look at, there are different peer-to-peer file sharing systems, different protocols, different software, different networks. We will look at one example, Bittorrent, next week. Okay? So next week, our last week, we will look at Bittorrent, see how that works, return back to our previous set of slides and look at distributed hash tables, and then we'll finish for the course. So maybe we'll finish on Wednesday next week.